Yeah, welcome back to next lecture on DSP, digital signal processing. In the previous, we have studied about the signals and classification of signals and systems and the classification of systems and what is the purpose of those systems and what are the different types of signals we have available. And now we are coming to the converting a continuous signal. Analog signal means continuous signal is nothing but is analog signal to a discrete signal. How it will convert? What is converting a continuous signal to a discrete signal is nothing but a sampling. It is nothing but a sampling. Sampling is a technique which is used to convert a continuous signal into a discrete signal. So for that purpose, we have a circuit called sampling circuit. If you see here, discrete time signals are often obtained by sampling continuous time signals, and this will be illustrated by this block diagram. Here, if you see x of t is having a sampling circuit, it is converted to x of n. X of n. So x of n equals to x of t at the t interval t equals to nt interval. So that is nothing but x of nt. If you see here the how it will converting the continuous signal. If you see here, for every time value, the signal is continuous with respect to the amplitude. If you see here, the every time discrete time values here and here and here and here, it is that the discrete time values on the x-axis will illustrate the discrete amplitude values. So that's why it is called discrete signal and this is called continuous signal. So for the purpose of converting the continuous signal, we will use sampling technique. This is the main technique which is used for converting the a continuous signal into the discrete signal. So what is the definition of this continuous? If you see here, converting a continuous signal to a discrete signal involves two main steps. One is sampling and another one is takes measurements at what is sampled. First we will see the sampling, which makes measurements at regular time intervals to make the signal discrete in time. So it has to make the signal from continuous to the discrete time. And quantization, which rounds these samples to a finite set of value levels to make the signal discrete in amplitude, creating fully digital signal. Means the sampling is nothing but whatever the continuous signal. Suppose I have 0 to 1 second, it will convert into the samples 0.01, 0.2, the discrete values, and that will be rounds by this quantization technique. So that is the thing here, the process of converting the continuous signal into the discrete signal. So why you're studying means actually the digital signal processing is in the digital signals. So but the continuous signal will be the analog processor, but in our universe the signal should be available in the analog manner. So we have to convert to the digital manner to get the more adequate values of the signals without any errorness. So coming to the continuation for that continuous and discrete time signal. If you see here, I just have given here examples of the continuous time signals and discrete time signals for an a unit step signal. If you see here unit step signal, all of you know unit step signal is nothing but a signal which will be available at t greater than or equals to 0 and t less than or 0, it will should be 0. Means at t, if it is, I am taking this is the t values and this is the amplitude value, means x of t value. I am saying t greater than 0 means t greater than 0 means here to here, equals to 0 means here, and greater than 0 means till infinity, and less than 0 means here 0 to minus infinity. So if you see here, the unit step signal is defined for only for positive values. If I take it, this is the amplitude 1 and 0.5, it will be give the step signal like this. Step signal like this. So if in this case for negative values, what is it is 0. So that's why it won't come. Okay. So how will represent this unit step signal in the continuous manner and discrete manner? If you see here, for t less than 0, it is continuously giving the signal. For same signal, here it is represented by the time t, whereas in the discrete signal it is represented by time n. So if you see here, the time u of n equals to 1 for n greater than 0 and u 0 for n less than 0. Okay. So here we will start give like x of n equals to means u of n. Here x of n is nothing but input signal is the unit step signal. So x of n equals to 1 comma 1 comma 1 comma 1. Like that we will see. So this is the brief intro about the continuous signal to discrete signals. So what we will use? The main two techniques are sampling and quantization. So these two techniques are very important in this role. Okay. So next, it is another signal which is used for which is indicates a continuous signal and the discrete signal. Already you know about the unit ramp function. What is ramp function? It will define for t greater than or equal to 0 and 0 for t less than 0. Similarly, in the time of n also like that. So it is like nothing but a linear curve. What are the values of x values is there with respect to x value, y value will be changed. If it is changes by 1 unit, it will also change by 1 unit. It will change by 2 units, 2 units, 3 units, 3 units. Like that, it will form a ramp curve. So the unit ramp curve is like this. So how the discrete signal will be represented in the unit and continuous ramp is here have illustrated. So thank you. Next, linear constant coefficient difference equation. What is linear constant? That is previously this is enough. This is about the continuous discrete and discrete signals. So this is linear constant coefficient difference equations. So what is the purpose of linear constant coefficient difference equation? So why you are coming? This is next topic of this unit. So actually, analog signals are represented by differential equations. But here we are studying about digital signals. Yes or no? We are studying about digital signal. So but you don't know how to represent a digital signal. For that we are using difference equation. So what we are using? Difference equation we will use for representing any type of digital signal. But whereas in analog signal it is represented by a differential equation, means d square x by x of t by dt plus dx of t by dt plus x of t equals to 0. Like that we will represent. But in this here we will represent by a difference equation. What is difference equation? Nothing but it is like a difference between first sample and next sample, because here you know what is the sample value. So if you coming to the definition of linear constant coefficient difference equation, linear constant coefficient difference is a fundamental in digital signal processing for describing how discrete time transforms inputs to outputs. How discrete time will be transformed from input to the output, means the discrete how the purpose how the signal will flow in the discrete time input signal to the output signal, expressing the relationship between current and past inputs and past outputs using fixed coefficients, enabling system analysis and filter design. So and recursive computations also. The model system like accumulators and the crucial for understanding stability and frequency response via Z transforms. And coming to the general nth order LCCDE equations, linear constant coefficient difference equations. In short form, we will call LCCDE is a equation, and it can be represented as summation k equals to 0 to n ak y of n minus k equals to summation m equals to 0 to m bm of x of n minus m. You can represent any represent our own here one of the type. And what is the purpose here? Y of n is the current output sample value and y of n minus k is the past, because it is delayed by minus k. So that is why past output sample and x of n is the current input sample and x of n is the past input signal and ak bk are the constant coefficient of the defining the system. So this is the linear constant coefficient difference equation. And if you coming to the solution for the linear constant coefficient difference equation, coming to the linear constant coefficient difference equation, the linear constant coefficient difference equation can be written as in the generalized form is y of n equals to y of n equals to minus summation k equals to 1 to n ak y of n minus k plus summation k equals to 0 to m bk x of n minus k. This is the equation for a linear constant coefficient difference equation. Already I have like explained what is y of n, what is y of n minus k, and what is x of n minus k. So for this we have to find the solution. So for this type of signals, the solution of the differential equation is in the form of yp y of n equals to yh of n plus yp of n. What is yh of n and yp of n? Yh of n is a homogeneous equation and yp of n is a particular solution. So the combination of homogeneous and particular is nothing but the general solution for this LCCDE equation. So how to find this homogeneous equation and particular solution? So y of n. So basically we will call the solution of difference equation is a natural response of the system. So for every system, the natural response is obtained by keeping x of n equals to 0. So if you're coming to here, how it will be changed from x of n equals to 0 means how if you keep x of n equals to 0, how it will change, we'll see. So here the equation x of n equals to 0 means what will happen? Summation, this one will be vanishes. Summation k equals to 0 to n ak of y minus n minus k is the remaining. So summation k equals to 0 to n ak y of n minus k equals to 0. So if you elaborate this equation, here also 0. So if you elaborate this equation, what will happen? So if I elaborate that one here, if you see here, I'm keeping k equals to 0, a0 y of n minus 0 equals to 0. Like that I am keeping f2 and third. So if you see here, what will happen? A naught y of n, a naught y of n plus a1 y of n minus 1 plus a2 y of n minus 2 plus up to so on an y of n minus n equals to 0. So let us assume for getting the solution purpose. For getting the solution purpose only, we are assuming that y of n equals to lambda power n and a naught equals to 1. So if I substitute y of n equals to lambda power n minus means y of n minus 1, what will happen? Lambda power n minus 1. Like that y of n minus 2 equals to lambda power n minus 2. If at like that y of n minus n equals to lambda power n minus n. Like this we will see. So by substituting these all these terms into the above difference equation, what will happen? Lambda power n, because y a naught is 1 and y power n is lambda power n, plus a1 y of n minus 1 lambda power n minus 1, plus a2 lambda power n minus 2, plus a3 lambda power n minus 3, plus up to so on an lambda power n minus n equals to 0. So just I am commoning these lambda power n minus n. So what will happen to here? Lambda power n plus a1 lambda power n minus 1 plus a2 lambda power n minus 2 plus up to so on equals to 0, plus an is remaining. So I am commoning this term into the whole equation. So what will happen here? Lambda n is there, but lambda power n minus n is not there. So if I commoning lambda power n minus 1 from the whole equation, so what will happen? Lambda power n is if I common from lambda power n minus n means there is nothing but lambda power n into lambda power n minus n. So that's why here we will get lambda power n after commoning the lambda power n minus n. So for the above equation, for this equation, the solution is in the form of characteristic equation having roots lambda 1, lambda 2 plus lambda 3 up to so on lambda n. These are the solution for the difference equation. For that we need a for that we have three types of roots. Basically for this type of characteristic equations we have three types. One is case 1. If these roots are case 1, roots are distinct and real, means suppose lambda equals to 1, 2, 3 means these are real roots but distinct means different roots we have. For that purpose y of n equals to means yh of n homogeneous equal solution is c1 lambda 1 power n plus c2 lambda 2 power n plus up to so on, because the lambda 1 lambda 2 are different solutions. So case 2. So what is case 2? Case 2, coming to the case 2, if the characteristic equation repeat the same lambda 1 means lambda 1 equals to 1, lambda 2 equals to 2, lambda 3 equals to 1 means these two roots are repeated. So repeated, then the particular solution yh of n equals to lambda 1 power n. Which one is repeated? Like that you have to write c1 plus c2 n plus c3 n square plus up to so on cm n power m minus 1. Okay, if it is case 3. If the roots are complex roots, then what will happen? You have to substitute lambda 1 equals to complex means a plus jb and lambda 2 equals to a minus jb. So where we have to write characteristic equation complex roots yh of n equals to r power n a1 cos n theta plus a2 sin n theta, where a1 and a2 are the constants and theta equals to tan inverse b by a and r equals to root of a square plus b square. These a1 and a2 are the constants. So this is the solution for the linear constant coefficient difference equation, and this is the solution only for the homogeneous equation. So what about the particular integral? If you see here, next we will see about the particular integral. So according to the particular integral will be depend upon the input side, means whatever the input I have given, according to that the output will come. So for that we have a table for what solution we have, what general form for the equation x of n. If you see here, I will see here x of n input signal and yh of y particular integral, so yp of n particular solution for that input. Here no derivation will be no need, just they will give directly what is the particular solution for which input. So if a it is a step signal. It is generated a constant k, and similarly a into m power n, and it will give k into m power n, and similarly a into n power m, means here the step signal is multiplying with n m and m power n, and here n power m, so it is nothing but k naught plus n power m plus k1 n power m minus 1 plus up to so on. So similarly a power n power m an into k naught of n power m plus k1 of n power m minus 1 plus up to so on. So similarly for a cos omega n and a sin omega n, c1 cos omega n plus c2 sin omega n. So these are the particular integral solutions for different input. So this step signal with multiplied with mn and n power m, an and a cos omega n plus and b sin omega n is same, c1 cos omega n plus c2 sin omega n. So this is about the solution for the linear constant coefficient difference equation. So in this linear constant coefficient difference equation we will study this thing. So in the next class we'll study about how we'll perform the problem on this linear constant coefficient difference equations, and what is the magnitude response and frequency response of the equation. So like that we will see in the next class. Okay, thank you.